When we left Lorenz in the last video, he was trying to figure out what trajectories could do in higher dimensional space. He'd observed in his weather models that something complicated was going on. The simple behaviors we see in two dimensions weren't enough to explain it. So he set out to create a system in three dimensions that exhibited the confusing, chaotic behavior he'd seen. And he succeeded. We're not going to study the Lorenz equations. We can't, but I'm going to put them up to drive home the fact that to look at them, they're not particularly complicated. dx dt equals negative sigma x plus sigma y. So that's just linear. dy dt equals rho x minus y minus xy. So this isn't linear, but these xy terms also appear in the Lotka-Volterra equations and the SIR model, both of which we successfully analyzed. And dz dt equals negative beta z plus xy. What happens to an initial condition under the influence of this system? Well, it's a bit like an asymptotically stable orbit. But the trajectory doesn't approach a circle or an ellipse or anything like that. What shape does the trajectory approach? Well, this thing. This is called the Lorenz Attractor. It's also called a strange attractor. It's called an attractor because trajectories are attracted to it, and it's called strange because, well, look at the thing. Almost 70 years later, the exact properties of the Lorenz attractor are not perfectly understood. In addition to being strange to look at, the Lorenz attractor exhibits the butterfly effect that Lorenz was looking for. Consider two initial conditions. -8, 8, 27, and -8, 8.00000001, 27. Let time run. By t equals 40, this initial condition has reached 8.03, 2.61, 32.41. Well, this initial condition is now at -2.54, -0.64, 23.87. This tiny perturbation in one of the coordinates of 0.00000001 has resulted in drastic changes to where the system is 40 time units down the road. In this video, we looked at the Lorenz Attractor. The actual Lorenz Attractor itself is illustrative. It doesn't itself appear in weather forecasting or any other applications. Rather, it demonstrates the profound problems that can arise when trying to use differential equations to model complicated real-world systems. The best solutions to this are called stochastic. They accept that there are going to be elements of randomness in any situation, so they build randomness directly into the model. But stochastic models would be a course unto themselves.